So question 5, Charlie claims to have proved the following statement. The sum of a square number and a prime number cannot be a square number. Give an example to show that Charlie's statement is not true. We're doing proof by contradiction here, aren't we? No, proof by counterexample, that's it, isn't it? We're just looking for one example where it doesn't work. So you just got to try and think, can you come up with a square and a prime that gives you a square number? And the most obvious start point for this is to say that if we do 1 squared plus 3, that's a square number plus a prime number. That gives us 4, which equals 2 squared. And there we go, we've got a square plus a prime, and it's given us a square number. So there we go. There's the one example. 4 plus 5 plus 9 does it as well. 9 plus 7 plus 16 is another example. There were a number of examples out there, so that's quite nice. Quite straightforward start. Part 2. Charlie's attempt at a proof is below. And this is a bit more subtle. So assume that the statement is not true. There exist integers n and m and a prime p such that n squared plus p equals m squared. P, therefore, is m squared minus n squared. That's difference of 2 squares, so we can factorize it. P is the product of 2 integers, therefore it's not prime, which is a contradiction. Charlie's statement is true. Okay, and that would have worked as a proof, but what is the error that he's made in there? Well, he said that by writing P as the product of 2 integers, that means it's not prime. And that's the flaw, because one of those 2 integers could be 1. And of course every prime number is the product of 2 integers, 1 and the number itself. So that's where the flaw is. So when he says P being m minus n and m plus n implies that P is the product of 2 integers and therefore not prime. That's where it's wrong, because m minus n could be equal to 1, in which case the number would still be prime. Okay, that's the crucial bit. It could be minus 1 as well, actually, for that matter. Right, so part 3 said, given that 853 is a prime number, find the square number s such that s plus 853 is also a square number. So, so what we're saying here is that s is a square number. It's some number squared. And if we think about the process that we've just gone through, we're looking for n squared plus 853, so the square number, plus the prime number is equal to m squared. That's using the formula that Charlie had helpfully given us, which means that 853 is m squared minus n squared, which means it's m minus n times m plus n. If 853 is prime, that's an m there, as 853 is prime, m minus n must be equal to 1. Which tells us that m is n plus 1, and we can do a substitution. So 853 is n plus 1 squared, take away n squared, which is n squared plus 2n plus 1, take away n squared, which means 853 is 2n plus 1, and we're nearly there now, aren't we? We're going to take away 1 from 853 to get 852 and divide it by 2 to get n equals 426. One final thing, the question did say find the square number, and I found its square root. So s is 426 squared, which is, I've gone to the next page, 181 476. I think, is that right? Yeah. So you need it to actually end up with your square number at the end of it. There we go. I've done that in, I think, quite a thorough way, but that's the basic process for getting there. There we are.